Imagine a world where skies light up so brightly that you could read newspaper outdoors. Well, this isn't a scene from a science fiction movie. It actually happened here on Earth on September 1st, 1859. On that day, British astronomer Richard Carrington witnessed an extraordinary solar flare, a powerful burst of energy from the sun, which he meticulously recorded. It caused a disruption in communication because telegraph systems worldwide went haywire. A similar event occurred on August 4, 1972, knocking out long-distance telephone communications across Illinois. Then on March 13, 1989, a similar flare caused geomagnetic storms that disrupted electric power transmission from the hydrocubic generating station in Canada. In December 2005, X-rays from another solar storm disrupted satellite-to-ground communications and GPS navigation signals for about 10 minutes. These solar events not only disrupt modern technology but also create one of nature's most stunning displays, the northern lights or Aurora Borealis. When the charged particles from these solar flares interact with Earth's magnetic field, they travel along the field lines to the poles where they emit light as they collide with the Earth's atmosphere. By measuring the speed and intensity of solar winds, scientists can predict when these particles will reach Earth, giving us the ability to forecast when and where the auroras will appear. These solar winds are not just breezes but powerful vectors carrying immense energy across our solar system. And by measuring the velocity of these vectors, which are actually solar winds, scientists can predict the strength of upcoming geomagnetic storms. The faster and stronger these winds, the more intense and potentially disruptive the auroral events will be. This connection is key to understanding and preparing for the powerful effects of the Aurora Borealis. So how can we find out the magnitude of a vector? A vector is an object that has both a magnitude and a direction. To visualize a vector, imagine an arrow pointing from one point to another. The length of the arrow represents the magnitude, which shows how much force is being applied or how far something is moving. Direction of the arrow indicates the direction in which the force is applied or movement occurs. To find out the magnitude of a vector, we use Pythagorean theorem, especially if the vector is represented in a coordinate plane with horizontal and vertical components. The formula to calculate the magnitude of a vector with x and y components is given by square root of x square plus y square. This formula gives us the length of the vector, especially measuring the straight line distance from the starting point to the end point of the vector. Now, just like the vectors we use to represent forces and movements on a flat surface, solar winds are also vectors, but they are three-dimensional vectors. This means they have three components, one for each direction in space, up and down, left and right, and forward and backward. For this coordinate system, the origin is at the center of the Earth, and the z-axis points towards the North Geographic Pole. The magnitude of a three-dimensional vector with components x, y, and z is calculated using the formula square root of x square plus y square plus z square. This formula extends the Pythagorean theorem to three dimensions, providing the straight line distance from the starting point of the vector to its endpoint in 3D space. This is how scientists measure the intensity and direction of solar winds as they move through the space. In 2018, the Discover spacecraft measured the three components of the solar wind velocity at a location of 1.5 million kilometers from Earth. This table shows the actual NASA data for a series of Discover spacecraft measurements of the three components of the solar wind velocity. Now, using the three-dimensional magnitude formula, we can actually determine the total speed v of the solar wind on each date. And with this data, we can actually calculate the time it takes for these winds to travel from the sun to Earth. This allows us to predict hours in advance when the solar winds will reach us, giving us a chance to prepare for and appreciate the magnificent display of the Aurora Borealis.